I will go ahead and introduce our first speaker. We have Rishabh Mehrotra, who's a senior research scientist from Spotify, starting us off. So it's over to you.
Thanks, Shiva. Actually, I can hear myself. That's a bit weird. Okay, right. So we have about 20-25 minutes. How do we learn from limited labels and weak supervision data? I'm hoping you guys can hear me okay, because I just see an echo in my head. So.
Yeah, we can hear you. I can hear you anyway.
Thanks. Yeah, so I'm a researcher with Spotify. I did my PhD in machine learning from UCL, and more recently, I've been working a lot on machine learning for marketplaces. After talk, I also was fortunate to give at the MLconf New York version in March, when we used to have these in person. So you've seen the slide bunch of times, right? That like data is a new oil, but more recently, what we're starting to see that when we're talking about these large scale deep learning networks, then the training data is the new oil, essentially. So a lot depends on what kind of training data we have to train these models. And specifically, the modern neural architectures are very data hungry. They need large amounts of training. The manual collection and curation of this data is pretty infeasible because it takes a lot of time and expense constraints to collect this data at scale. And there is also dynamicity in the data generation process that the data is not stable and static, the distribution over time as well. So, and also you might have dynamicity of modeling goals, that your modeling goals may vary over a period of time based on the business strategy and the most immediate goals your team might have. So the question of learning from different amount of data which we have kind of is the main question which we want to tackle here. And specifically, well, the question we want to answer is like, how do we harness data for training machine learning models? So if you look at the labels, which are the main input, which treat the model in terms of like what kind of feedback do you want to update the parameters with, then one thing to identify is that not all labels are equal, essentially. So some may have more information than the others. So some labels might be more readily available. Some of these might be less readily available, while some could be very strong labels and strong supervision signals, whereas the others could be weak supervision signals. So this kind of brings forward the question that how do we learn from data which may not be that much? So oftentimes we have scenarios wherein we have very strong signals, but they're not in like millions and billions of numbers, essentially. So if you look at the specific examples, then in this talk, we're going to focus on two types of supervision signals. So the first one is the ground truth data, which is, let's say we ask users, how do they feel about some of the recommendations we give them, or we ask expert judges on some labels, essentially. So essentially, this data is not available in large quantities because collecting ground truth data from users is very expensive. But then this is a very strong supervision signal, because if the user is telling you, I liked or did not like this recommendation, then that's a lot more powerful than anything you can infer. On the other side, we have weak supervision data, which is a weaker form of supervision, and they may come in from a number of different sources. They are abundantly available, but they are very noisy. If you look at search systems, so search systems rely on clicks and dwell time as a metric of satisfaction. Recommender systems rely on engagement time and whether you're clicking or not. So these are heuristics and implicit signals from which these large-scale search and recommender systems are trained on. So again, like the point over here is that you often have large amount of data, but they are like weak supervision signals. You have a small amount of data, which are very, very strong indicators of user happiness and user delight, perhaps. So how do we combine learnings from these both when we train our large-scale neural models? So that's the question we want to answer. And let's just briefly look at what type of weak supervisions we are talking about. So it could be distance supervision, like often you have heuristic labeling rules, which you rely on it to task some data you might have. Or they might be weak classifiers, so they might be trained on non-expert crowd data. They could be biased classifiers that they're trained on data from some other different domains, but maybe like related. Indirect supervision, like you have a companion binary task for which obtaining the training data is a lot more easier. So you can use some supervision signals from that task, perhaps. You can have response-based supervision, or you can also have like constraint-based supervision, wherein you have constraints that are represented as weak label distributions. So again, like right now, I mean, we have a lot of tooling and machinery available to collect more and more forms of supervision signals, but then they're like very weak. So I can collect large scale data, but then like they're pretty weak. While at the same time, I can ask the users their explicit judgments, and they are very strong signals, but they are very rare in number. So I can train a large scale end-to-end encoder decoder architecture on just user response data, right? Because I might ask just like maybe 10,000 users for in-app surveys or for the labels, and I cannot train like a 100,000 parameters neural network on 10,000 training data example. So that's the question we want to tackle, that how do we combine the strong supervision signal and the weak supervision signal together? And this is like a part of this work was covered in a recent KDD paper this year, wherein we were working on developing some optimization techniques to do that. So as such, we have different types of strategies. The first type of strategies are like data strategies, wherein we try to combine data sets in novel ways and kind of train our models. But then we identify that there is a very limiting aspect to this, and that's why we want to go back and adapt our optimization strategies to better accommodate these new signals, that some of them are supervision signals while the others are weak supervision signals, perhaps. So if you look at data strategies, then let me just go through some of these. So the naive technique is the blue dots over here are strong data, but they're very less and rare. The red ones are weak supervision signal, which are like omnipresent, perhaps. So the naive combination is I just combine everything into one and just train my models. But again, like you might have unrelated examples, which might steer your gradient in the wrong direction. That leads to suboptimal training. So what I would want to do is like, I would want to carefully subselect the weak supervision data, which I use to train my models essentially. So how can we subselect these supervision data? So one of the examples of doing that could be like, I can have some similarity threshold. I only consider training examples which are closely related to the ground truth example I have. So I can have some similarity threshold to define which of these weak supervision data should I be incorporating in my actual training data set. The other example could be interleaving, that instead of an aggregate similarity, I can look at the representative training examples from my strong data set, which is very small. But then for each of these, I can go and look at the larger data set and subselect few of those and then bring it back to my main data set. So you can like interleave the strong data and some representative examples from the weak data and then create your data set together. So these are now viewed as more of a subset selection strategy as well. So here, what we do is we cast a problem as a subset selection problem, that we select the subset of most useful weak supervision data conditioned on what task do you essentially. So submodularity is a nice optimization concept which kind of exploits the property of diminishing returns, that like your friends, right? If you don't have any friends, then the first friend will be hugely valuable to you. If you have like 10,000 friends on Facebook, then addition of one more friend may not be as valuable to you, perhaps. So oftentimes these subset selection problems can be cast as submodular optimization problem. So again, like what we do here is like we view the training set selection strategy as a subset selection problem, cast it in terms of this specific submodular function, which is a combination of informativeness and representativeness. Informativeness in the sense that I want to pick up examples which are informative to my main model, which I'm these tell me exactly coverage they're good, that they cover the different types of training data set I might have. Again, like there are some of these ways of like mixing data, but essentially we want to be able to have more control in the learning process and not just in the training data set creation process. So again, like one of the ways in which we can do that is via differential weighted learning. So often when we are training these neural models, we rely on stochastic gradient descent or ADAM, the optimizer, which it's heavily used across the industry and academia for training these models at scale. Now, what we can do is we can modulate the parameter updates on a per data point basis. So the intuition over here is that if you have a strong data, then I will trust it more. I will say that I have high confidence in the label of this specific data. So I'll let it modify my parameters appropriately. But if the data is not that trustworthy, so I'm going to diminish the changes in parameters which it can do. So essentially what it looks like is that you follow your typical gradient descent momentum updates. You compute the gradients, you compute the first and second order of moments of your gradients, and then you adapt your learning rate based on the confidence you have on the specific examples. So again, this is where we encode the notion that if your data is coming in from strong data, which is very rare, but it's very, very trustworthy, so I'll let it govern the parameter updates. But then if the updates are coming in from data which are like weak supervision and they might be noisy, we don't trust that enough, then I'm going to take a step back and not allow it to do major changes to my parameter updates. So this approach is similar to a very nice and famous ICLR paper from Google folks around fidelity weighted learning. So if you're interested, there's a link at the bottom which you can refer to. Lastly, I want to focus more on how do we increasingly change the momentum adaptation itself. So if you look at Adam, then Adam relies heavily on momentum to give the parameter updates. So essentially, momentum simply adds a fraction of the previous weight update to the current one. And in general, momentum allows you to dampen the oscillations that if you have the gradient pointing in the same direction as before, so then you increase the steps you take towards minimum. But if gradient keeps on changing directions, then you try to smooth out the variations. And there's controlling the momentum of your parameter updates and gradients in Adam style optimizers is like a very active area of research as well. And a bunch of papers in recent machine learning conferences are looking at this problem specifically. So what we do is we apply the same idea we had, that if I have strong data, then I'll trust it more. And if I have weak data, then I won't trust it enough. So essentially what we do is like we know that Adam updates the exponential moving average of the first and second moment of gradients. So what we do is we dampen the oscillations, we dampen the contributions coming in from the weak supervision data, essentially. So we have a momentum update coming in from previous instance, and if the new instance is a strong supervision data, then I do not dampen the oscillation, the momentum coming in because of this. And if the data set is weak supervision, then we damp the contribution from the gradient update of the weak supervision data, essentially. And how do you dampen it? So then you can compute this momentum damping coefficient. And this is up to you. Like you get to decide if you have a label weight, that how much of a trust you have on this label, you can use that, or you can use some other like tagging techniques in which allow you to quantify the confidence you have in each of your training examples, essentially. So yeah, so basically what we do is like this gives us this momentum damped version of Adam. So it's Adam structurally as a backbone, but now you're controlling how much the momentum can dampen the oscillation based on how much you trust your training example. Again, the same intuition that if it's coming in from weak supervision data, then I won't ignore it, but I'll kind of give it a less weight, and I will dampen like the impact of it. But if it's coming in from strong supervision data, then I'll trust it more, and then I'll let it do what it wants to. So great. So just to summarize, the problem we are trying to deal is that I have large amount of noisy, weak supervision data, a small amount of strong data. How do we mix it? So we looked at a few data mixing strategies. We looked at a few adaptive optimization strategies. So let's see how it performs. So we do two case studies. So in the first case study, we are looking at the Spotify homepage and predicting user satisfaction on the Spotify homepage. And in the second case study, we look at a NLP task of visual question answering, essentially. So again, if you look at satisfaction prediction with recommendations, then your strong supervision signal, an example of that could be explicit user feedback. So maybe you show a pop-up on your homepage and ask like, are you happy with your current session or not? Are you happy with this recommendation or not? So this is user telling you explicitly whether they're happy or unhappy, right? So this is a very strong form of supervision signal. But then you cannot collect it for like 1 million users because you don't want to annoy 1 million users with your pop-ups. So this is the ground truth data, which is strong supervision, but then it's like rarely available. But then we also have weak supervision data, like your implicit signals, that have you spent a lot of time, dwell time on the homepage, or the number of, what's your session length, and how many songs have you played? So these are some examples of implicit feedback signals which we use, which can give us whether or not the user was happy or unhappy. we can collect it for like all the 120 million, 150 million users we have. But the problem is like, even though this is large scale available, it's pretty noisy because it's not very strong in terms of representing the user's actual happiness. So again, like if you look at this, then we can apply the same problem that we have a neural model, we want to predict user happiness. And then like I have two forms of supervision data which I can use, and I can apply the techniques which we just talked about in order to train my model. The second example is video question answering. So here, the goal is you have a video and you want to find answers to a specific question. Again, like you cannot have judges watch 100,000 videos, right? Because that's very, very time consuming. So you can get some sort of data from your Amazon Mechanical Turk studies, but this is like strong data, but very limited available. Or you can use some existing Q&A data set from Wikipedia, the Stanford Q&A data set, perhaps. So this is distant, not directly related to task, but then it's form of weak supervision data which we have available. And then like the model we have, attention model, the details are in the paper, but then essentially the same problem happens. Like we have two sorts of data sets, and how do we learn together from both of these? Reserve the last 2-3 minutes for Q&A. In the meantime, if you want to type in questions in your on chat, feel free to do that. Right. So if you look at the impact of weak supervision, so just looking at like, what if I just use my strong data, just weak data, or combine it in naively, right? So then we say that if you only train on your weak supervision data, then it's okay in the video Q&A, but it starts to hurt in your user satisfaction task. And in general, like adding ground truth, which is a strong data set, it's useful in both the cases essentially. But one of the key takeaways is that if you're using your weak supervision data naively, then it may not always be helpful because that's very noisy. And often if you're using it without any proper intelligence, then you might just kind of detract the learner from learning the right things essentially. So what carefully which weak supervision data we want to use for models. So again, we find across the spectrum for both the tasks that similarity or interleaved strategies perform better than just using the ground truth data. And interleaving is slightly better than just selecting based on similarity, and submodular subset selection is better than each of these. So essentially, the takeaway message here is that if you're careful in how you select your data, by select your data, I mean like how you select the weak supervision data, which you want to merge with your ground truth, the strong data, then it can help you improve performance. But more interestingly, what we find is that adaptive training, like the momentum damped version of Atom and the differentially weighted version of Atom, they kind of perform better than all of these strategies. So again, like we found for both the tasks, they give better performance. And in general, the adaptive optimization techniques are more useful in increasing performance. So just a couple of other minor points, like, again, like how much of weak supervision data do you want? Or how much can you easily get and how much of it is useful? So maybe there is like, you don't need to maybe consider all the different 10 million weak supervision examples, and then maybe you start seeing some plateau effect. So in the paper, we also slightly talk about that based on the domain you have and based on your problem setting, you might need some large scale data sets of weak supervision, or maybe some of these are enough. But more importantly, we showed generalizability of this method. That right now I showed you two different tasks. Now, user satisfaction prediction with recommendations and video question answering are completely two different domains, right? And here we are seeing that if you're combining your weak and strong data, which is very intuitive, which is very obvious, that why shouldn't I be doing that? But then like how you're doing it, we're seeing that some of these methods of adaptive optimization are useful across these like two separate tasks, right? So perhaps there is a lot of generalizability across tasks as well. And also there is generalizability across models because the question answering model is a gated neural retention model, which is completely different from the simpler feedback aware neural model, which we might use for recommendation purposes. So again, this is my point and pitch that perhaps looking at adaptive optimization is helpful even if you have tasks which are not exactly these tasks. If you have like multitask recommendation models or like maybe a more sequential recommendation models, then perhaps like we might be able to leverage same techniques in your downstream application modeling task as well. So messages that we should look at developing these frameworks for learning from weak supervision wherein we want to jointly leverage the strong and weak supervision. And there's a variety of approaches to choose from. So again, like if you're starting off, if the maturity of your ML teams are not that high, then perhaps we don't want to go to momentum damped techniques. Perhaps you can just look at some simpler techniques of data mixing and subset selection and get my wins. But then if you want to increasingly get more and more wins, then perhaps you can swap in and swap out your Adam optimizer and get the gains which you need. We looked at some different ways of data mixing strategies, and just the fact that blind combination is not enough, carefully subset selection is nice, and it's kind of pretty helpful in increasing your performance. And of course, like the adaptive training is pretty useful. So you can adaptively tune the learning rate or kind of have momentum damped version of it, wherein you are very careful in how much of your parameter updates you're allowing your weak supervision signals to have an impact on, essentially. So yeah, so that's the end of the talk. You can find me on Twitter, but I'm happy to take questions. So I'm going to look at the screen on the other side to pick up a couple of questions if there are there. So Sean has a question. What if your strong and weak data separate along positive and negative labels? For example, what if all or most of your supervision examples from weak data? That's a great point. So again, like this, look, I mean, a lot of these scenarios can happen wherein like your weak data is perhaps not distributionally matching your ground truth data, right? So if that's the case, then we should rather look at can we generate more weak supervision data from maybe some other sources. So if you look at some bias classifiers, or if you train, so let's say if you look at a semi-supervised setting wherein like you train a model, let's say on your ground truth data, and then make that predict for your weak supervision data, the labels, the negative labels, which perhaps you might not have in your weak supervision data. Again, like you can use some sort of like indirect supervision wherein you train a model separately and then generate new training data and then try to combine those data sets. So Mike has a question. Does it make sense to limit the amount of weak data that we use in relation to the amount of strong data? Actually, yeah, that's a good point. We did find evidence that in some of the experiments, just unnecessarily polluting the training examples with unrelated data set, that kind of hampers the performance gains which you can get. And we're seeing that in the results as well, that like, again, like people do this early stopping, right? I mean, you want to be able to avoid overfitting, or unnecessarily, you don't want to keep on learning not useful aspects of your model. So again, like we are starting to see plateauing effect of the weak supervision data, and sometimes like performance starts decreasing if you cross that threshold and if you start polluting with like unhelpful examples in your training set.